rapidly grown into a leading center of academic excellence and innovation. It is currently ranked 344th globally in QS World Ranking 2025. IIT Guwahati is widely recognized for its cutting edge technology research, world class faculty, and the strong industry collaborations. So, beginning with this, I would like to give a brief introduction on IIT Guwahati Society of Petroleum Engineers student chapter. Our chapter strives to create a vibrant platform that broadens opportunities for students through technical, professional, and community oriented activities. By organizing lectures, workshops, and industrial interactions, the chapter aims to bridge the gap between academic research and real world energy challenges, especially in the emerging fields like low carbon technologies and sustainable operations. And likewise, you may be pleased to think about. Further, today it's a pleasure to introduce Mr. Rahul Jain, who currently serves as Vice President and General Manager at Computer Modeling Group of uh, ours. With over 18 years of experience in technology and energy simulation domain, Mr. Jain has a strong track record of transforming strategic vision into impactful execution. In his role at CMG, he is responsible for driving the core business profitability, defining and executing the product portfolio roadmap, leading go to market strategies, and managing CMG's global capability centers in India. His leadership plays a key role in advancing CMG's mission of pioneering dynamic reservoir simulation and production technologies, particularly in the context of new energy transition and CCUS solutions. So it's pleasure to have you here, sir. I would like to hand over the stage to you now. Please begin the session.
Thank you, Chitra. Thank you so much. All right, I am going to start sharing my screen and I'll just need a quick raise of hand that you guys can see it. Just give me a second. Chitra, can you see it?
Yes, sir.
Yes, sir.
Perfect. Perfect. Thank you. What a beautiful morning here in Bangalore, and thank you for such a warm introduction. I'll take some time before I introduce Dr. Vijay, but I'll just start with probably just a quick overview of what CCS technologies and the landscape looks like. And as all of you as all of you know about CCS, let me start with a very simple thought. If we are serious about climate change, we cannot ignore CCS. And if we are serious about CCS, we cannot ignore simulation. And today's session is about connecting these two, carbon storage and the technologies that help us design it safely and at scale. Now, many of you here are students, right? So you are entering the industry at a very fascinating time. I think the next 5 to 8 years would define whether CCS stays as a very niche solution or it becomes a mainstream one. But let's start with where we stand today, right? Globally, if you look at it, we have around 77 CCS facilities that are currently in operation, and they capture roughly 64 million tons of CO2 per year. Now, if you ask me, that is impressive. But if you look at it, what's needed by 2040, we need to capture around 4 billion tons of CO2 every year. And that's not a typo, it's a billion with a B. So to get there, we also need approximately 2,500 CCS facilities, each injecting about 1.5 million tons CO2 per year. So from 64 millions today to 4 billion, that's a massive scale up. And it just won't happen because we want it to, right? The scaling of CCS is not just a technology problem. Otherwise, people in this room, Dr. Vijay, and so many other industry professionals would have already solved it if it was just a technology problem, right? We need good reservoirs. We need storage access. We need supporting government policies. We need shared infrastructure. And something that we don't talk about enough is the international collaboration. You would see that the future CCS hubs would mostly be the cross-border projects. You are moving CO2 from where it is being emitted and taking it to a different location, different geography, different country where it can be easily stored. And this is where I think, because of this international collaboration and the scale, this is where engineers, modelers, scientists would come in and play a very important role in scaling CCS to that 4 billion tons by 2040. Right? But see, the other challenge that you will run into, one of the uncomfortable truth that you should remember is across all the projects that are currently operational, we are seeing a recurring pattern. Almost 10 to 20% of our CCS projects are underperforming. From what was forecasted early on, there's a degradation of the performance almost by 15 to 20%. And if you wonder why is that, because there are things the performance reduces because of some invisible factors at the very beginning. And I'm talking about the pressure buildup, temperature changes, seasonal effects, flow limitations in wells and the pipelines. So if I simplify that, it's like a slow leak in your car tire. Nothing happens abruptly, nothing happens right away, but over time, the journey becomes inefficient. And that's what is happening. That's what's crippling the CCS projects, a lot of CCS projects globally. So why does simulation matters, right? This is an area where if you only simulate the reservoir, you miss what's happening at the surface, right? You miss simulating the compressors, the pipelines, the temperature changes, the pressure constraints. And if you only look at the surface, you miss what's happening deep underground. So in my mind, CCS is one system. It is a fully integrated system all the way from capture to transport to injection and storage, as well as monitoring. And all of them has to be one connected system, right? And as more projects move from planning stage to real operations, siloed modeling across each of these functions will not work. You need an integrated modeling from surface to subsurface, and it is a necessity. It is not a luxury anymore as we move from planning to operation stages. Right. Now, before I hand this over to Dr. Vijay, right, I want to leave you with a quick preview of what really makes CCS work underground. Right? All of us are engineering students, petroleum engineers. We know that when we inject CO2 underground, it just doesn't disappear, right? It gets trapped underground through multiple mechanisms. You have the structural trapping, where your cap rock acts like a seal. You have the residual trapping where CO2 gets locked in the pore spaces. You also have solubility trapping, right? As CO2 gets dissolved into brine. And then if you look at longer time frames, there's mineral trapping where I would say CO2 literally turns into a rock. And and as you know, CO2 behaves very differently underground, right? It changes phase, density, mobility as there are changes in pressure, temperature, and salinity, right? And to make it more complex, then you have to add geochemical reactions. You have to add the geomechanical effects. You have to consider the injectivity limits. And because it's CCS and you're storing it underground, you have a need to continuously monitor and verify that the plume is spreading as you planned it to be, right? That's why if you consider all of these changes, CCS is not a single discipline problem. And that is where I think numerical simulation becomes the backbone of CCS, because it will help you test all of these mechanisms, the trapping mechanisms, the geochemical reactions, the geomechanical effects. It helps you manage those risks. It helps you design projects that would actually perform as planned. without any degradation of the injectivity performance that you have claimed or that you have planned. So with that, I'll hand it back to the SPE chapter so that they can introduce Dr. Vijay, who's going to explain these concepts in depth and tell you how we can use them in modeling real CCS projects. So with that, probably I'll give it back to Chitra or Priyanshu.
Thank you. Thank you, Rahul sir. It was really insightful. Thank you. So now I would like to introduce our second speaker. It's an honor to introduce Dr. Vijay Srivastav, Principal Engineer, Compositional Simulation at Computer Modeling Group Limited. Dr. Srivastav has been a key contributor to the advancement of carbon dioxide storage and compositional reservoir simulation technologies at CMG. For over 2 decades, since 2003, he has led the development of critical simulation workflows within CMG's compositional simulator GEM, enabling comprehensive modeling of carbon dioxide solubility, chemical equilibrium, mineral reactions, absorption, diffusion, and dispersion, caprock integrity, well-bound reservoir interactions, and geomechanical effects such as fault reactivations during carbon dioxide restorage. His extensive expertise and contributions have played a pivotal role in shaping the state of art CCUS simulation technologies, of course. And we are privileged to have him share his knowledge with us today. So please, Dr. Shivasu, please begin.
Thank you, Chitra. Let me share my screen here. Are you able to see this?
The screen is not visible, sir.
Okay, is it visible now?
Yes, sir. Now
Okay.
it's working.
Thank you, SP chapter of Society of SP chapter at the IIT Guwahati for giving us the opportunity to share our ideas that we have developed over the years with many people here. And this is the agenda of the talk. We will look at what is CCUS and what are the prerequisites for modeling CO2 storage, what are basic physics behind it. And this talk is designed for students and researchers and faculty members at IIT Guwahati primarily. So please bear with me if I come up with certain equations in between. I don't want to make your morning heavy, but that is a necessity here. So Rahul already covered the various facets that are involved in CO2 storage. Here you can see on the right-hand side, we have a well that is injecting into a reservoir. What happens in CO2 storage, that you inject CO2 for a period of time, for instance, say 20 years, 30 years, 50 years, and leave the CO2 there for it to be there or move wherever it could go. So the business of doing simulation is optimizing that process so that your CO2 remains underground. It doesn't go to the areas where you do not want it to go. As pointed out, the enormity of CO2 emissions and requirement for us to meet the goal is quite challenging. And as we are talking about 350 to 400 sites for CO2 storage are under development. And as time passes, we will see that more and more operations coming up throughout the world, including in India. And that I learned that they have made a beginning in Gandhar, the Dahej field. So here you can see where we can store CO2. This is a primary slide that basically telling you that if you have an oil and gas reservoir, you can use CO2 for enhanced oil recovery. So you can inject CO2, CO2 goes, gets miscible, you can produce it, produce the oil, and you can improve your recovery. Or if you have large amount of CO2 is available, you can inject it underground in deep saline aquifers. So you can leave it there, but after it has been injected, it is going to move. It is not going to remain that in that place. So we have to find such traps which help us containment of the CO2. So we are able to inject CO2 and make sure we are getting rid of it for longer period of time. Next, we could have a depleted oil and gas reservoirs. Here, you can utilize the facilities that are available to you, wells, other infrastructure, and inject CO2 there. Or you can also inject CO2 in unminable coal seams, where CO2 goes, gets absorbed on the surface of the coal, displaces methane, and you get methane gas as a byproduct. Now, this table tells you what is the storage capacity that we have over all throughout the world, globally. So saline aquifers consist of about 90% to 98% of capacity, and oil and gas reservoirs are the next one. So in this talk, we are going to restrict ourselves to these two locales where we are going to see what happens when we consider CO2 storage there. Now, this is the big picture of what we call CCUS, carbon capture, utilization, and storage. You are seeing something on the surface here, and there is a cross section that so you can see also underground. So normally we are looking at oil and gas operations where you produce the gas. It can be stripped of CO2 if the CO2 content is high, and it can be re-injected right away in a formation for improving oil recovery or simply for storage. The other possibility is that you send it to consumers that are going to use your gas. And of course, there will be some emissions there. You have to capture that. The other possibility is that this natural gas goes to industrial areas, and oil and gas production can also bring this amount with this natural gas to our industries. Similarly, there could be gases coming from biomass or from coal production for use in different, there is possible use of this gas. You can make electricity or do petrochemical plants or cement factories, so on and so forth. And net result is that they are going to create a certain amount of CO2. And sometimes it is quite heavy that calls for its sequestration or remediation so that CO2 in atmosphere is reduced. So we bring it to something called CO2 hub. And from this hub, you are going to take your CO2 to different areas, to storage sites, to further industries. There are also industries that use CO2. For instance, there is mineral carbonation can happen if you send it to a specified place, or you can ship this CO2 through tankers to larger places where there is a scope for injecting CO2, and you can inject underground. So the bottom line is you have a big network here that is collecting CO2 and trying to mitigate it, trying to sort of sequester it or store it underground, and thereby reduce the footprint of CO2. On the right-hand side, you will see the network of pipelines, transportation pipelines, gathering centers, capture sites. They all will bring the CO2 to the place where we are going to inject. And these are three wells that are shown here. So the CO2 eventually reaches there and it gets injected into the reservoir. So this is model of a reservoir that you can see these three wells are going to inject. depending on their capacity and depending on the constraint that we set in this network. So you will realize that modeling this whole process becomes a challenging task if you want to optimize the process, minimize your costs, and have a good design for CO2 storage. So beyond this, now we are not going to talk about capture and utilization. We will talk simply about the CO2 storage, which is the topic of this talk. So let us see the physics involved in CO2 storage. We have an aquifer here. This big part is an aquifer, and here it is overlain by a cap rock. And when you inject CO2, it can come in gas phase, or it can come in liquid phase, and it will interact with the aqueous phase. It will dissolve in there, and the thermodynamics is going to create a equilibrium here. So part of it gets dissolved, part of it remains undissolved. Then there are aqueous reactions that will take place. Those are reversible fast reactions that will take place. There will be reactions on the surface of the minerals. For instance, you have calcite that reacts with hydrogen ions, and it produces calcium ions and bicarbonates. So after these things have taken place, apart from these, you will see that there is flow of CO2 also going to happen along the aquifer. Now, see, and if you continue injecting, it is also possible that there is stress development, and because of that, could be possibility of leakage. So you see the amount of work that is required here. You need some geochemists to understand what is the reactions, how the reactive transport is happening. You need thermodynamics guys to understand what is going on with equilibrium. You need kind of geomechanical people to understand how the overlying rock is getting weakened and how it is going to allow CO2 to escape and how to prevent that. So there is a multidisciplinary activity that is involved in tackling this. So in the end, the objective of numerical simulation is to design safe, secure, and long-term storage of CO2. And after we have stored CO2, challenge is to monitor where CO2 is going to go. We don't want to pollute our potable aquifers or affect the population. And there are in every region, you have some regulatory requirements that needs to be met. So if you are careful in your simulation, you can meet each of these requirements. For instance, in India, you have Directorate General of Hydrocarbons. In Alberta, you have Alberta Regulatory Authority, so on and so forth. So we need to meet those requirements, and simulation comes handy when it comes to specify and meet those challenges. This is the structural, this is different kind of trapping that Rahul talked about. So I'm not going to go into further detail, but explain this picture here, which tells you the increasing storage security with different mechanisms. The structural trapping traps the gas or CO2 in physical form. You see its amount reduces as you go in time. This axis is time in logarithmic scale. So you can see over large number of years, structural trapping is going to reduce. Now I am going to turn on my light. Please bear with me. Okay, so next one is residual trapping, which is because of relative permeability of gas and hysteresis effect. This also over time develops and gets reduced. Then there is solubility trapping, dissolution of CO2 in aqueous phase. And you can see how this amount changes. And finally, we see the mineral trapping, which develops at a very slow rate, but it persists for a very long period of time. So if you wanted to get rid of CO2 for a very, very long time, very long period of time, mineral trapping becomes very important to study for us. Now we go further. For modeling of CO2 storage, you need to understand the thermodynamics. Multi-phase, multi-component equation of state is required. You need to understand the solubility in aqueous phase and what is its effect on salinity. And finally, geochemistry. So on this side, you will see that this is temperature and density is plotted on y-axis and viscosity in the second graph. So you can see that unlike other gases, CO2 is quite difficult to handle. It can create two-phase region in this part here, where the density has a lot of discontinuity. And these discontinuities bring us challenges for us in doing our simulations. Your convergence is going to be very challenging in this area that needs to be specifically handled. And same thing goes with the viscosity. Now, we were talking about relative permeability. Here you can see you are injecting CO2, your gas saturation is increasing. So your relative permeability of gas follows this path as you go on injecting gas. After your injection ceases, after you have stopped the injection, your plume starts moving outwards. And during that period, at the point where you injected, saturation of gas is going to decrease. But this need not follow the same path that you went while injecting. This is called hysteresis effect. And because of this hysteresis effect, about 40% or 20% in some cases, this gas gets trapped, and this is called residual trapping. Now, other important thing is to consider is diffusion and dispersion. After you have injected your convection currents, convection means velocity of gas. It reduces and practically comes to very, very small amount in certain areas. And there diffusion and dispersion kicks in because, because of very low flow rate. Now, another thing you will see is we have listed here dynamic gridding. If you are modeling this reservoir, if you have the ability to adapt your grids according to the front that is moving, then you are going to save a lot of time, because larger the grid size, it is going to take as much less time, because your number of grid blocks are reduced compared to if you had to sort of simulate it at a fine grid. Next, you have to also do the energy balance and geomechanics as we go and see in the next slides. So coming to thermodynamics here, we have a phase envelope. Pressure is on y-axis, temperature on x-axis, and this is pure CO2. You can see the phase diagram. Here is triple point, here is the critical point. And in atmospheric conditions, CO2 is in gaseous phase that you can see here. When you are transporting CO2 through pipelines, it is normally in liquid phase. But when you are injecting CO2, most of the time it is in supercritical state. So you will see this plays a big role in how we simulate and how we define our properties of CO2 or CO2 with impurities in this supercritical region or in this transition region that happens all the time. This is again called narrow boiling phenomena. Just like you have a pot of water, you heat it at 100 degrees C, it will take some time before it turns into vapor. So liquid turns into vapor at a constant temperature. So similarly here, when CO2 is in liquid state, it takes at constant temperature, you have two phases developing, and here entire CO2 vaporizes. So this is called narrow boiling effect, and this is important for us to handle in our simulations. Now, what happens when you have mixture of CO2 with other gases, or you have some impurities in your CO2? This is pure CO2 there is no envelope here. This is pure methane, there is no envelope. We are going to change the concentration of methane here, for example, and thereby the concentration of the mixture CO2. So CO2 is 80%, CO2 is 60%, 40%, so on and so forth. So this phase envelope is moving towards left. And because of phase envelope movement, number of phenomena will take place where liquid is, where vapor is. They will all get decided because with the phase envelope that you have got here. This is a more complicated scenario where this is again PX diagram, mole fraction on the x-axis, pressure on the y-axis, and you have one liquid here. There is second kind of liquid that you can see, liquid and liquid two equilibrium is there, liquid and vapor, liquid, liquid vapor, and liquid vapor equilibrium. Where this happens in say miscible floods, or if you are doing CO2 storage in depleted oil and gas reservoirs. So there it becomes very important to understand and tackle. Look at the challenge here. Your density, if you are passing the boundaries, your densities are going to change rapidly. Your interfacial tensions are going to change rapidly. So if you have a good handle on that, you will be able to make a good prediction. If not, there can be problem in the prediction. Now we look at the solubility. These are different correlations that are available in different simulators that you would see. And on the right-hand side, you will see the effect of salinity on CO2 solubility, which is at different pressure and temperatures we have plotted here. So if we pick up, say, two constant temperature, 25 degrees C, 25 degrees C, temperature pressure increasing from 1 MPa to 10 MPa, you can see there is increase in solubility. Similarly, if you pick up two pressures, two constant pressures, say 1 MPa here, 25 degrees C, go to 100 degrees C, there is reduction in solubility. So this is the effect of NaCl molality on aqueous phase solubility. Similarly, when you are injecting CO2, CO2 gets dissolved in brine. Brine becomes heavier, and because of that, there is density change in the water. The brine that is dissolved with CO2, it will change its density. And as the pressure increases, you will see the density is going to increase with increasing amount of CO2. Now, this is a result of a simulation where you can see that 3 wells were here where CO2 injection was done. Because of change in the densities and the viscosity and mobilities, convective currents formed, and then the plume migrated outwards. So we have to account for these change in properties. And over the years, this plume is going to migrate outwards. So that is the challenge of the engineer to forecast where this plume is going to go. Another phenomena that happens during CO2 storage is water vaporization. If you are injecting CO2 in a brine or in a saline water, water vaporizes from there. Because of the thermodynamic equilibrium, there is possibility of water vaporizing and thereby salting out effect happening near the wellbore. This reduces injectivity and it can be considerably reduced. And there is a project in the place where I live in Alberta, Canada, where there is a project called Quest. It is a cell-operated CO2 storage project. And in year 2020 to 2023, their injectivity in 3 wells fell down by, it reduced to 10% of whatever it used to be earlier. So they had to go in for remediation of, they call it halide precipitation, which is nothing but salt crystals. So remediation is easy. You have to inject water with biocides and is oxygen scavengers and all that. And then they found that the injectivity improved. And this was predicted by simulation and designed through simulation and uh, transient testing. So pressure buildup, pressure follow-up test, and the reservoir simulation came handy to remediate the situation. Now we are talking about chemical equilibrium and mineral reactions here. Chemical reactions and fast and reversible reactions, and they are characterized by equilibrium constants. Mineral reactions, on the other hand, are slow. They are governed by TST reactions. They take long time to materialize. Now we will look at the flow simulator formulation. Basically, you have component mass balance equations, phase equilibrium equations, column consistency, and energy balance equation. When we talk of mass balance equation, it is simply a housekeeping of how much you are injecting, how much you are producing, and how much is remaining in the reservoir. So this equation basically tells you that. And if we talk of phase equilibrium, there is something called fugacity, which our chemical engineers are very, very familiar with. You calculate the fugacity of a particular component, CO2 in this case, in the phases that you have. And equality of fugacity means you have created equilibrium, so you can predict how much solubility of that particular component is going to take place. The volume consistency, it is simply telling that all your pore space is occupied by different fluids that you have. And this forms the backbone of your pressure equation. So you are solving pressure by making sure that your pore volume is completely filled with fluids. And energy balance is similar to flow, but here convection of energy, conduction, and net energy production or injection and heat loss, they make total accumulation. And I will go in little detail about this equation for the benefit of the students and researchers. Please bear with me. It is not going to be very, very difficult, but I am going to venture in here. So basically, mass conservation is a convection, diffusion, this is sourcing term, and the reaction rate. So change in moles over time, we are telling that this is because of convection that you have, because of diffusion dispersion, and because of the your sourcing term and reactions. This is simply Darcy velocity that you can see the potential here. It includes capillary pressure, capillary as well as gravity forces. So you have something called mobility here, which is nothing but absolute permeability multiplied by relative permeability, that becomes your effective permeability divided by viscosity of that phase, that becomes your mobility. So this terms goes in here, and there is something called transmissibility, which you will see on the next slide. This is area of the phase. If you have a grid block of del x, del y by del z size, the del y into del z is your area. And this term is called transmissibility if you divide it by the distance between two nodes. Okay, so now we will write these equations for the solubility in terms of finite difference. You can see the terms here. This is contribution of oil phase. This is contribution of gas phase. And this is the contribution of the component that is going in the aqueous phase. And this is your simply accumulation term. So we are making this equal and including how much injection production is taking place. And this is written over all the components that you have. Now, one thing to take into consideration is this M, which is denoting the time stage as you are. If you are having something what they call it implicit solution, this is your current time denoted by n plus 1. If it is explicit, it is denoted by n. So you have to judiciously select your time label. And there are other variations I'm not showing here in further detail, but need to consider that if you have implicit, that means every variable is at current time, it is more challenging problem. You are solving all the equations, whereas if it is explicit, you are solving only your diagonal terms. Your IF diagonals are not required to be solved. This is the equation for water, where you have again transmissibility of aqueous phase and the accumulation of water. And this is again injection and production term. Now, there is a relationship between total number of moles and number of moles that go in aqueous phase. And this is determined by Henry law constant, which is given here. And if you have fugacity, you can calculate how much of uh, CO2 or the dissolved component is going to go into aqueous phase. So you get this relationship, and this Henry law constant comes from experiments at infinite dilution at a reference pressure. You can convert it, having known it at a particular reference pressure, reference temperature, you can convert it to a pressure temperature at which you are going to operate. Now we will go a little bit in chemical equilibrium reactions. The reaction is simplest reaction is written here. So there is something called equilibrium constant, which is basically activity of the product of activity of your product divided by activity product of the reactants. And this is available at different temperatures. For example, I picked up at 50 degrees C. This comes from databases. And so we are going to utilize this in our reactions to find out how they will take place. Going into activities a little bit further, activity of water is 1, and activity of a component is determined by activity coefficient multiplied by the molality of that component. There are different models for getting this activity coefficients of species. Normally, B dot and Pitzer models are used in the industry quite often. Pitzer model is for quite involved model, and this is used for saline brines. Now, having got the activity products and equilibrium constant, we can set up the equation. We can say that our this activity product, we go 1 to number of aqueous components that are there, right? That, and this is your stoichiometry of that particular component. And if you multiply them together, you get this Q of that reaction J. And this is equilibrium constant of reaction J. So if they are equal, you are good. You have to solve this equation to find out what is the rate of that reaction. And in this case, there is no rate because this is an equilibrium reaction. So you have to simply make them equal to satisfy the equilibrium. Now, in mineral reactions, you have, for instance, calcite, which is going to react with hydrogen ion, produces calcium ion and bicarbonate ion. The rate is defined as change in moles, and this is grid block volume divided by time. So you know how much moles per time your rate is. And this needs to be equal to volume. This is reaction area, reactive surface area. This is rate of the reaction, and these need to be equal. This Q is again activity product of these two guys divided by this. For calcite, the activity is assumed to be 1. And this one is called saturation index. If your saturation index is larger than 1, there is mineral precipitation. If it is less than 1, there is mineral dissolution. So now this last equation, which is energy balance, that you can see again transmissibility is written here in finite different form. And you have this transmissible heat goes with the flow. the enthalpy is carried by the flow. Then you have the conduction term. You have amount of enthalpy coming in or going out, and there is heat loss. And this is equal to your accumulation term, which is given by this term here. This is your rock heat capacity. This is rock density, porosity, and initial temperature and current temperature. This is enthalpy. And then this is the contribution of work done by the pressure. So basically, if you set up this equation, it is possible for you to solve for pressure, enthalpy, moles, and temperature. Now, apart from when we write these equations, we also need to worry about the boundary conditions. Initial condition is that everything is in equilibrium in layman's language, and boundary conditions are defined by the wells with which you operate. So with that, we will form a set of equations for each grid block. Your domain is discretized into number of grid blocks, and each grid block is going to have as many components. Now, to give you an idea, supposing you had a implicit solution and you have, say, 8 components. So 8 into 8, you will have 64 equations to solve there. For implicit solution. If you have explicit, it would be diagonally you will count your off diagonal terms will go away. So for each grid block multiplied by number of grid block, you can imagine the number of equations that you have, and then they are linearized and solved with high performance computing resources that you have got. This is another important thing to know, that if you are doing CO2 storage, supercritical region, it is difficult to find out whether it is gas or liquid. So we do something called Wiedem line. Left of the Wiedem line is liquid, right is gas. Now we will come to geomechanical effect. You see CO2 is being injected into this. There are stress changes. And because of those stress changes, number of things can happen. There can be pathways of fractures through which leakage can take place. There can be faults that can get reactivated. So it is important for us to study the geomechanics. Now I'm going to discuss this a little bit about this workflow. You have data from the laboratory. You have geophysical data, geological data, and petrophysical data. Combine them together, make your reservoir model. Similarly, you will have geomechanical data, and you have initial stress distribution. With that, you will make your earth geomechanical model. So when you are taking pressure steps, you are going to calculate pressure, temperature changes, and that you can pass to geomechanical model. It will calculate the resulting porosity and pass back to you to account for in your porosity permeability model. So this is called coupled geomechanics. And in between, you are going to visualize and see how this simulation is happening. If you want to do this simulation all by itself, is standalone, so there is one-way coupling. This loop goes away. And this is now we are coming to illustrate some examples. This is an aquifer where there is CO2 injection being done. It has nice permeability and porosity. It is overlain by 2 cap rocks here. One is here, another one is here. And there is hardly any permeability. So these are sealing cap rocks. But as your injection takes place, you will see with, if you are not careful, it is possible that you can rupture this cap rock. You can rupture this cap rock also with time. That is shown here in this particular example. This is time, and this is cumulative CO2 moles. You can see in this big aquifer, you injected this much amount, but after 500 years, there is degradation or a weakening of this cap rock because of stresses that got developed, and this gas got leaked. So you have gas going there. After further moment in time, you will see that this cap rock also gave away and this CO2 escaped. And if you have not designed your process well, it is possible that CO2 can come to the surface after you have injected. It did not remain there because of the geomechanical geomechanical changes that took place and took away your seal. Now we are talking about near wellbore phenomena. This is the CO2. This is diagram of a wellbore, not to the scale. You can see CO2 can come in liquid or gaseous form. As it comes through the choke, it expands. So there can be Joule-Thomson cooling. There can be hydrate formation here. And as it passes through the tubular, there can be a lot of corrosion, erosion. Many things can happen. There can be explosion or many things are happening here. That means thermodynamics is continuously changing in this tubing. When it reaches the perforations, there are things that will happen here as well. So we need to take this total scenario into account, including the reservoir, while modeling the effects. And we have to design our tubulars so it becomes important for us to do what we call transient wellbore modeling. And transient wellbore modeling, that means you are doing the simulation at a very, very small time steps. Time steps are in seconds here. So you can see as you are injecting CO2, there is large variation in pressure that can happen. So your tubular should be designed in such a way that they can withstand the shock that is created by this kind of change that will happen in the wellbore. Now we will look at a CO2 sequestration case, which was for a field located in the North Sea. It is a Sleipner gas field. And from there, gas is produced to the surface. And then it is injected in a overlying aquifer, which is called Utsira formation. So we inject CO2 and we are going to see what happens there. So this is part of the model that we are showing. There is a CO2 injector here, and we are going to see how we can model it and what you can see. So in this picture, you are seeing as CO2 is injected, it is in gas form. It is injected, and your currents are convective currents are forming here. As CO2 goes down, you can see there is some formation of minerals as well with time. And CO2 is moving outward also. It is going downwards because of gravity, but it is also moving outward. And the outward movements become prominent after the CO2 injection has taken place and you left it uh, there for some time. So now this is the period where you stopped your injection. And we are going to see here how much CO2 went in different phases. So this is called inventory of CO2. And CO2 is in gaseous form. You see it reduced over time. This is in aqueous phase. It increased with time. And this is bicarbonate that also increased. And if you look at the minerals, this is 2,500 years. You can see the calcite flux dissolved and then precipitated. Kaolinite precipitated and anorthite dissolved here continuously. And this is inventory. You can see the distribution of these places where CO2 went. What is their distribution over 600 years or 1,000 years? And finally, we are going to see a case study in Gulf of Mexico, where we are showing you the faults as you are looking from the top. This is trace of the fault, and there is a CO2 injector here. As you inject CO2, if your rate is not very well designed, it is possible that CO2 can migrate towards the faults. And those faults, if you are not careful enough, it is possible that leakage can take place through those faults. So this is the cross-section view. This is YZ, this is XZ, and this is YZ cross-section. Here you can see the fault traces are shown here, and your well is injecting here. CO2 went here, and after certain period of time, there was possibility of the CO2 to escape through this fault plane. So it came to the surface. So that means you have to design your rate in such a way that you avoid this condition. And this is to do on your computer, and you don't have to do in the field. So it is easy for us to design that rather than do an experiment in the field, which could be quite expensive. Now we are looking at monitoring, measurement, and verification. There are a number of operations take place during pre-injection phase. You need to find out what is your aquifer extent, what are the properties, brine properties, and so on and so forth, and where you are going to locate your injector so you can have good injectivity. And after it is injected, during injection, you find out how your pressure drops are happening in your well. Is there any injectivity impairment or not? And after injection has ceased, you are going to monitor your plume, where it is going to go. There are physical means, there are modeling means, and there are other techniques to find out where the CO2 actually went. So each time you are simulating and doing its validation. Without validation, your simulation is of very little use. So let us see what are the challenges in CO2 storage. You have a domain here where you have to be very, very fine to resolve the changes that are happening near the wellbore. As you move outward, you have large areas to cover where the CO2 can go, and you have to find out if aquifer is going for 20 kilometers, what happens after 5 years or 20 years or maybe 500 years, how far the CO2 that you injected here, it is going to go. And this uh, added a scale dimension. That means we have to be quite concerned about the smaller scale and also the larger scale. And you have to carry out your simulation in a time which is practical. So how to design that your simulation model is a challenge. And over the years, you will find number of CO2 storage studies have been done. And in reality, number of storage sites have provided you data. So it is possible to leverage AI and through machine learning techniques and find a faster solution than what we comes with the conventional reservoir simulation. So I come to the concluding side. We discussed all the physical mechanisms involved in CO2 storage, geochemistry and geomechanics, the intricate physics, and we realized that it is a multidisciplinary activity, so no one discipline is good enough for it. And there is a lot of research going on as we talk about to improve our simulation technology. There are many, many weak points that those needs to be improved. And this is a picture from a site, Quest site, that I discussed a little bit before. And there, if you go, they have two arrows here. This is a big arrow which says up there, too much CO2 is a problem. And this arrow shows deep down, there we have a solution by CO2 storage. So this brings to end of my talk, and floor is open for question and answers, and basically for idea exchange. That's what I want to say here.
Vijay, thank you. Thank you so much, Dr. Vijay. Fantastic.
Thank you. Thank you so much, Dr. Vijay.
Okay, I hope I did not exceed the time frame that was given.
No, no, not at all.
Okay.
Not at all. We really appreciate the time and the effort you dedicated to providing us with a set of knowledge. I hope that the students attending this meeting, they would be triggered with a lot of questions. So thank you for joining us. And now we will take some time to address your questions live. Please proceed if any of you have any question.
Yeah, I would like to invite questions from experienced people as well. who are, if they have joined this webinar, I would like to get their ideas, learn from there. And so this is a kind of idea exchange, not only passing the knowledge from one side to the other. So I'm here to learn from you guys. So please feel free and come up with your questions or your comments or whatever you have.
Good morning, Dr. Vijay. This is Dr. Sumit from IIT Guwahati. Thank you for accepting our invitations and giving us the time for today's webinar. So last year, one of my MTech students did one solubility modeling with Duan and Son, also with the Henry law. But this Henry law and Duan and Son could not match. Also, Duan and Son and the other further model couldn't validate it at higher molarity. So, what could be the issue with Henry law and the Duan
See,
and Son and the
yeah,
Caesar at the higher molarity?
yeah, Duan and Soon is more accurate model for high saline brines, okay, and higher temperature. If your temperature is higher, Henry law is not that good. But Duan is quite accurate at higher temperature. That's what our comparison showed. So, and there is a modified Henry's law correlation. If you have seen, it was done by Harvey. So he tried to address some of those deficiencies that were there in original Henry's law. So try using Harvey's Henry law correlations, as also, if possible, use Duan. And nowadays, people also use this mutual solubility that is proposed by Spicer and Proust model. You know, yeah, Spicer and Proust is used by many, but there is a limitation that you could have only one component that is soluble. If you have impurities, then that model is not valid.
These Spacker and Proust and the Duan and Son use a very empirical equations to model the density of CO2, and this is true for pure density. So, how the two model will be implicated when impurities are there in the CO2? Is it validated or some issues are there?
See, if there are impurities, it depends on how much impurities you have. If they, for instance, if they are more than, say, couple percent, they are more than 5%, then there is another equation of state people try, which is called Gerg equation of state, GERG, if you have heard. So that gives quite good prediction. But trouble with those models, Span-Wagner or Gerg model, is that they require large number of parameters. Spicer and this Span-Wagner requires 52 parameters, whereas you have only 2 parameters in Peng-Robinson. So it becomes it becomes very challenging to model to sort of model and run it a practical simulation with that.
Okay, thank you. I got the idea. I will try to implement your suggestions.
Okay, thank you.
Very good presentation, Vijay. It's Marathe from your friend, old friend.
Thank you, Dr. Marathe.
I'm delighted to see you here.
If you guys at IIT Guwahati are familiar with him, he used to be director of Institute of Reservoir Studies. And I'm sorry, I'm going to turn my light on here again.
Marathe sir.
Yes.
Okay, so please, Dr. Marathe, please go ahead, and I look forward to your ideas. Yeah.
Very, very good presentation, and I was really super excited to know about you going to present on a very exciting topic. My only suggestion, or whatever you say, is to have a small discussion on relative permeability and capillary pressure hysteresis and the impact of that hysteresis on the plume migration, because I think it's a very important effect.
Exactly. You hit the problem on its head. I tell you a story. In Santos Basin, Petrobras has a very big project coming up. About 10 megaton of CO2 is targeted to be injected there. And they are very much in hysteresis modeling, primarily because they run water and WAG,
Technical energy
water alternate
sciences
gas.
and allied
And
disciplines developed by
also,
various institutions and organizations and countries. They are not by the enthusiastic participations.
And
uh,
so,
okay, so they have carried out laboratory experiments at pressure and temperature conditions that exist in that basin. That is, I have not seen that happen anywhere. And actually, they invited me there. We worked with them for a couple of months and then try to understand what happens when hysteresis is there. So you are very correct. There should be a talk on hysteresis alone. That this topic doesn't do justice to hysteresis modeling.
Just one small addition, because one of my
Yeah.
ONGC colleague is also here and I am with him. There is a lot of excitement on injecting CO2 in basement reservoirs.
Yes.
If you can throw some light on that, because yes, there is a good chance of sequestering CO2 in basement.
Yeah.
This is
Yeah.
from one of my friends in ONGC, and I'm
Yeah.
very glad that he has raised this question. So if you
Yeah.
can throw
Actually,
some light.
I am reminded of one field from Vietnam. It is called Tiger Field.
Yeah, white tiger,
And
very famous. Yes.
exactly. And that one is actually basement. In they tried to do some injection long time back. It is 5 or 7 years back. They had come to us and they tried to do. I am not fully aware what is the outcome of that, but definitely if you can inject and store CO2 in basement, nothing like it. It is deeper and it is
Yeah.
going to be there for a very long time.
Good.
Your
Thank you.
reactions definitely will play a big role there.
Thank you very much.
Any further questions?
Dr. Vijay, this is Dr. Sumit again from
Yeah.
IIT Guwahati. So, related to relative permeability, what critical aspects connecting with the hysteresis you would suggest me to capture during the core flooding study?
See, the thing is that your saturation can continuously change. It can go up or down, and your relative permeability doesn't follow that unique path. It can reverse or it can have scanning curves. There is
Right.
a paper by Ernie Skaja of 1996. I mean, that gives quite detailed description of the hysteresis process. And if you are interested, please send me an email. I will find and give you some material to work on
Sure.
it. And
Another,
yeah,
yeah. Please finish yourself, then I'll come.
yeah. So, and of course, there are many kilos model, lands model. There are many models for hysteresis. And as Dr. Marathi rightly pointed out, it deserves its own session for discussion. And it is very important, especially in CO2 storage.
Another one, quick one. What is the core length effects when we do study relative permanent hysteresis? Really implicated on the practical data which would translate to the simulator. So, is there any effect of core length that we
Of course,
capture?
I mean, I have never had opportunity to work in the lab, so my answer may not be very accurate. But what I have seen in Petrobras laboratories, they have a long, they have pieces of core put together about a meter long or so. So I don't know if that is the way people go or there is some different way. I have very little idea in that area.
Okay, great. Thank
So
you.
long back in IRS, we used to do the same thing. We used to stack cores one over the other
Yes,
and
yes.
prepare a long core pack. In fact, a core pack. But sir, my submission here is mainly to capture the hysteresis. You don't require a very long core. You can do it even in a small core.
Mhm.
And as Dr. Vijay pointed out, it's more important to get the scanning curves from the lab data, which will be very useful to model the hysteresis part. In fact, in this connection, I have a nagging question for a long time in CO2 sequestration projects, particularly in saline aquifers. Would it not be prudent to have some aquifer wells to produce water in between for a few duration to induce this wettability reversal? Because if you
That
produce
is,
water,
yeah,
yes,
that is very
and don't allow the pressure to go up.
that is a very good idea for us academics, but I don't
Yeah.
know how it will be taken by the operators because
Yeah,
there
that I
are
agree with you. Yes.
yeah.
But as it is, the economic model of CCUS is always a problem.
Definitely, definitely, and it is driven by the concessions that you get from the government. There is tax break or this break, that break, that
Yes.
actually is promoting the research in CCS. For
Right.
example, DOE is spending billions of dollars on CO2 storage research, and that is a very good thing to happen, and not many governments have that luxury of spending so much in research.
Thank you. Thank you.
Good morning, sir. Sudev Kundu from Dehradun.
Hi Sudev, how are you?
Fine, fine, sir. Sir, I have one query to know how to model the saline aquifer CO2 injection and the simulation of saline water CO2 injection, sir. So what we are facing, sir? Suppose in a simulation model, initially that was entirely water phase and we are injecting the carbon dioxide. So normally we are giving the water gas relative permeability. But once the reaction starts,
Mm-hmm.
the
Mm-hmm.
third phase, that is the aqueous carbon dioxide comes into play.
Yeah,
So, are you using another phase relative permeability to mimic the entire process, or you are
yeah.
doing something else, sir?
Okay, okay. Very good question. Actually, when you do the CO2 storage, it is always recommended to have your oil, water, and gas relative permeabilities. That means you have your oil, water, and gas liquid curves, both of them you input. The reason is that the CO2, you never know when it can condense, depending on the situation. Even if it is pure CO2, it is possible that you want to use liquid curve because it has turned into liquid. In some software, it will be called oil. So with that, you are able to use the correct relative permeability. If you don't have it, then of course it is not a correct representation. And when you are talking about reactions, there is interpolation of relative permeabilities that is possible. Like you have two sets of relative permeability, and based on a particular characteristics of the reaction, you can interpolate. You can do kind of little bit of history matching and see that okay, if I had this kind of reaction rate, I had to use this permeability, relative permeability, which is in between this set and this set. So interpolation of relative permeabilities people do consider. And for general use, of course, you have all the three phases present all the time as far as input data goes.
For interpolation
So
between the two set of relative permeability, definitely I have to provide a relation with the carbon dioxide
say,
concentration in the
yeah,
aqueous phase.
yes.
How
So it is possible to say if your say dissolved CO2 amount is so much, you shift the relative permeability from this curve to other curve. So depending on the component concentration, you can switch your relative permeability. And I don't know if you are aware, there is a paper by UT Austin, Gary Pope. Gary Pope is the name of the author. If you search for that, you will find he talks about compositional dependent relative permeabilities. So that is something to follow, and it will give you an idea. And Mr.
Thank
Kullu,
you,
you
sir.
are from Dehradun, is that right?
Yes, sir. Yes, sir.
Is Kumar Sweets still there at Ghantaghar, or is it gone?
Yes, sir. It is still present here, sir.
Okay, okay. I remember I have been there long time back.
But they have expanded their business surrounding the Ghantagar.
Okay, okay. Very good.
Thank you, sir. Thank you.
Further questions? Or I think we can stop here, sir. So
Yeah, I think Chitra has a question, and
okay.
she must ask one. Chitra, can you ask your question, please?
I'm sorry, sir. I didn't have a question. I was just talking
No,
about
ask
that.
any question. Ask any question that you want to ask.
Okay. So, sir, I always think about only one thing: how to dive into it. I'm very new to this field.
Okay.
I don't have prior knowledge about it. How should I proceed knowing about it? How should
Well,
I?
it's a very, very good question. And as a student, I mean, we are all students all the time. So we must learn physics, chemistry, and maths, and everything revolves around it. That's what I would say. And if you are in chemical engineering, that is a very good branch. You will study transport phenomena. You will study how the fluids change through thermodynamics. So you are in a very good state of managing CO2 sequestration in your career later on.
Okay, sir. Okay. Actually, I was new to chemical field only. That's why I wanted to know that. Thank you so much, sir. Thank you so
Yeah,
much.
yeah, definitely. It is very exciting journey if you want to pursue that.
Right. It is. Thank you, sir.
Thank you.
Yes, sir. So as we conclude this webinar, we extend our sincere gratitude to Dr. Vijay Srivastav and Mr. Rahul Jain for graciously accepting our invitation and for sharing their valuable insights and expertise we have with us. Also, sir, if it is okay, we would like to share this whole seminar to our students also for their knowledge also. So is it okay for you?
Yes.
It is okay. And actually, you will see I have referred to many papers in the slides as I go along. So those are actually the work that we have done over past 20, 25 years or so. Uh, so it is all in public domain. So feel free to distribute. And my boss here, Rahul, can give you an advice on that one.
Yeah, yes,
Rahul,
Priyanshu.
please.
Yes, Priyanshu, you can share. No problem.
Okay,
No problem
okay,
at
sir.
all.
Okay, and also we would like to thank our faculty advisor, Dr. Sumit Kumar, for his guidance and support and appreciation towards the dedicated efforts to all the student organizer and team members and those who has ensured the smooth conduct of this webinar. IIT Guwahati SP Student Chapter sincerely acknowledge and thanks all the students, research scholars, faculty members, industrial professionals who joined us from various diverse departments representing various institutions, organizations, and countries. Your active participations and engagement greatly enriched this section. With this, on behalf of the entire organizing team, we formally conclude today's session. Thank you all once again, and we look forward to your continued support in our future events. Thank you. And
Uh, yeah,
okay.
thank you very much. And on from CMG side, I would like to say that we need your collaboration. Collaboration is very important. So Mr. Rahul Jain is our boss in India. Please be in touch with him. And we are certainly going to get newer ideas from newer younger generation, and that we want to sort of advance the simulation science. That is what is in our interest. Thank you very much. Thank you for the invitation.
Thank you.
One more
Mr.
question,
Jain,
sir, I wanted
yeah.
to ask. I'm sorry, am I barging in?
No, go ahead, please.
No, go ahead.
Sir, I was looking for a internship or any job opportunity to work in a specific field that you stated today in your webinar. How should I proceed with that?
My boss is here. Ask him, not me.
Oh, okay.
Chitra,
So
we
the
can
question
connect.
traverses.
We can connect offline. You have my contact details, or Biswajit has my contact details. You can email
Absolutely.
it.
Okay, sir. Thank you so much. Thanks again.
Bye.
Thank you so much, sir. All right.
Okay. Thank you. Time to go.
Sir, good night.
Good night.
This
Good
is
night,
late
sir.
night for you.
Bye.